Hello everyone. I'm excited to present our work titled Contact-Aware Amodal Completion for Human-Object Interaction via Multi-Regional Inpainting. This research is being presented at ICCV 2025 in Honolulu, Hawaii. To begin, let's distinguish between two key perceptual concepts shown in this diagram: modal and amodal completion. Modal completion, shown in the top half, is when we perceive a shape that isn't optically present, like the illusory triangles here. The completed area is visible. In contrast, amodal completion, shown in the bottom half, is how we perceive an entire object even when part of it is hidden or occluded. The part we mentally fill in is invisible. Our work focuses on this challenging task of amodal completion. Specifically, we focus on amodal completion in the context of human-object interaction. In this example, a person is sitting on a chair, partially occluding it. Our goal is to predict the full, complete appearance of the hidden parts of that chair, a task essential for robust scene understanding. Occlusion in human-object interactions presents unique challenges compared to static scenes. The visible parts of an object can form concave shapes or multiple disconnected segments. However, these interactions also provide a powerful cue. The contact points where a person touches an object give us strong information about the spatial relationship between them. This brings us to our contact-aware amodal completion framework. We introduce a novel approach that leverages physical common sense to guide a powerful diffusion model. The key steps illustrated here are: first, identifying the occluded region in the input image, which we use to create a multi-regional inpainting mask that guides the final completion step. The first core step is occluded region identification, where we use physical priors. We define two regions. The primary region is an area where the occluded part is highly likely to exist. We generate this by applying a convex hull operation on the boundary between the human and the object, along with the contact points. The secondary region is the rest of the occluding human, where the object is less likely to be but could still exist. Once we have these regions, we perform multi-regional inpainting. This is our new inpainting technique that applies different denoising strategies to the different regions we identified, without needing any extra training. As shown in the diagram, this process takes the input image, our primary mask, our secondary mask, and a text prompt, and intelligently fills in the missing areas. Our denoising process is controlled by a strength hyperparameter, R. In the early denoising steps, the model establishes the core structure of the object by denoising only on the high probability primary region. Then, in the later steps, the model refines the details by denoising on both the primary and secondary regions. This two-stage approach ensures the generated structure is physically plausible. Here, we see our experimental results. Qualitatively, our method generates more plausible and coherent completions across various objects compared to other state-of-the-art methods. Quantitatively, our method achieves a mean intersection over union of 77.64% on the Behave dataset and 72.34% on Intercap, an improvement over all prior work. This slide shows the effect of the strength parameter R. A lower value for R, such as 0.1, guides the model to mainly denoise on the primary region, resulting in a more constrained completion. A higher R value, like 0.9, allows the model to denoise on both the primary and secondary regions, showing the controllability of our framework. The impact of our work extends to downstream applications, such as multi-view 3D reconstruction using 3D Gaussian splatting. As you can see by comparing the images, the 3D objects reconstructed using our completed views are far more complete and contain fewer artifacts than reconstructions done without our method. Our method enables novel post-synthesis with 3D Gaussian splatting. By creating a complete 3D model of the object, we can render the human interacting with object. Here is another example of novel post-synthesis. The ability to amodally complete the occluded object is critical for creating these consistent and realistic animated sequences. In this final example, we again see how our completion enables robust synthesis of new interactions. In conclusion, we've introduced a novel, contact-aware framework for Amodal completion. By leveraging physical priors to guide a multi-regional inpainting process, we achieve state-of-the-art results that benefit 3D vision and synthesis applications. Thank you for watching.